So the first thing I want to do is almost give you the characterization. I'm going to give you one side, and then we'll take a couple of more corollaries and stuff to get the if and only if. So what I'm saying is that, first of all, using that theorem, which again, it's hard to appreciate it. I don't know. It really is nice that you found a divisor that C minus, any one divisor, C. Like it's an invariant of the function field, like G. So that for any A, the dimension of this space is exactly what was missing. But it's not clear yet how really great this is. So this is me? No. It wasn't like a, right? Good, yeah, I was. You don't want to record it again. So let's see be a canonical divisor. Then I claim that we know the dimension and we know the degree. I mean, given the genus. I mean, we know that all canonical divisors are the same degree and dimension because they're in the same class, but that's the degree and that's the dimension. And what we'll show afterwards, after the break, is that this is an if and only if. And that's great, because then now if you want to find a canonical divisor, we just need to find a divisor with that dimension and that degree. So the proof is really easy, just plug in zeros here. So let's see. So by Riemann-Roch, so this is Riemann-Roch. Let's plug A equals 0 to see what happens, right? Because when I plug A equals 0, I'm going to get the dimension of C. You see from here? So set A equals 0 in Riemann-Roch. So you get the dimension of 0 is the degree of 0 plus 1 minus G plus the dimension of C minus 0, which is just C. And that's great, right? That's it. So the degree of 0 is 0. The dimension of 0 is what, by the way? For fun? 1. Yeah, 1. And that's it. You see, so the 1 cancels. So G goes to the other side, and you see the dimension is G. Good. Now, as for the degree, you see, if you want the degree of C to appear here somewhere, you need to take A to be C. So let's do that now. So now set A equals C, again, in Riemann-Roch. So you get that the dimension of C, I'm just copying it, plugging A equals C, equals the degree of C, which is what I want, plus 1 minus G, plus the dimension of C minus C, which is just, this is the 0 divisor. Right, I just plug C instead of, and we know that the dimension of C minus C is 1, because that's the dimension of 0 divisor. And we just computed the dimension of C to be G. From here, that's why I did it in this order. And then you can extract the degree, right? Yeah, so you need to move things around. Right? You move this G and this plus 2, get to G minus 2. Good. So you see, for Riemann-Roch, you immediately kind of got information. Maybe you will say, maybe there are other divisors with that degree and that dimension, but there aren't other divisors. We're going to prove that now. But as a starter, let's prove another claim. I will state it and we'll prove it after the break. Generally speaking, what we are trying to do is using Riemann-Roch to map divisors, like to understand if the degree is high enough or small enough, what can I say about the dimension or something like that. So in this claim, what we are going to do is to handle the low regime. We're going to do the following. But we'll prove it after the break. So if A is principal, it has nothing to do with Riemann-Roch. I think this was or could have been in the homework. Okay. So if A is principal, then the dimension of A is 1, and the degree of A is 0. Actually, we know that. That's obvious. Because if A is principal, then you can just take it to be 0. Because the degree and dimension don't change when you move from a principal, when you add a principal divisor. So if you start, right, so the 0 divisor is a principal divisor, and all principal divisor has the same degree and dimension as that 0 divisor. And we know that the dimension of, this is a proof inside claim, dimension of 0 and 1, and degree of 0 is 0. Right? And because we know that, and we know that the degree and dimension don't change within a class, so that's already new. We already know that. The interesting part, again, not like interesting, but not like Riemann-Roch interesting, just a little bit of logic, is that you can ask whether there are other degree 0 divisors. Like principal divisors of degree 0, whether there are other ones. So if the degree is 0 and A is not principal, well, there can be other like that, but then the dimension I claim is 0, not 1. Like principal divisors are example of degree 0 divisors. And then you know also that the dimension is 1. But you can ask, what other degree 0 divisors do I have? Not coming from functions, not principal. Then what you can show is that if you have a degree 0 divisor, which is not principal because you understand the principal ones, then what I can say is that the dimension of those is 0. That will prove after the break. Yeah. And from there we go to the, so this is the low regime, the low degrees, degree 0. Riemann-Roch allows you to move from 0 to the degree of C, essentially, to 2G or something. And that will allow us to handle the higher degrees and to prove the equivalence. Okay, let's take a break. Right, so it really has nothing to do with what we're doing right now, but I need to do it. So, okay, so I'm going to kind of prove the contra in some version of a contrapositive. So the logic is the only hard part here. So I'm assuming that deg A is 0, and I want to prove that if A is not principal, then the dimension is 0. Okay, so I'm replacing this end with an arrow, the same thing. So assume the degree of A is 0. That's a fixed proof. And now I want to prove that if A is not principal, then dimension is 0. But I'll prove the contrapositive because it's nicer. Because once I'm going to prove that if the dimension is larger than 0, it can be smaller, right? If it's larger than 0, then it's not principal. Then it's principal. And it's easier because it's hard to start working with a negative. It's easier to work with something. So if I know the dimension is positive, there is an element in the Riemann-Roch space and I can do something with it. That's the point. So the proof is as follows. So assume dim A is non-negative and of course deg A is 0. So that's the given, and I'm going to doing the contrapositive given the given. Then what does it mean? Then it means that x plus A is non-negative for some x, which is non-zero, for some function. Right? Because if the dimension is larger than 0, it means that there is an element in the Riemann-Roch space, x, that is non-zero. And because it's in the Riemann-Roch space, this one. Right? This is just because this tells you that, and that tells you this. Right? There is a non-zero x in the Riemann-Roch space, and being in the Riemann-Roch space means that. But then the degree of x plus A is the degree of A, right? Because degree doesn't care about this principal divisor. The degree of the principal divisor is 0. It's something that we proved. And that's 0 per assumption. Right? So you have this divisor is a degree 0 divisor, but it's also a larger or equal than 0 as a divisor. So it's a degree 0 and everything is non-negative. So because of that, we know that x plus A is the 0 divisor. Right? You can't be always positive and have 0 degree at the end, unless you're already 0. There are no minuses to cancel out. So this is the case. And so this means that A is this thing. namely A is principal. X wasn't 0, so I can do this inversion. Right, and that's what I wanted to prove. Assuming that the degree is 0, it's kind of confusing, but it's nothing really. Assuming the degree is 0, the dimension is larger than 0 implies you're not principal. Implies that you're principal. That's what we did. That's really as an exercise. Maybe I shouldn't have done it even. But that allows us now to do using Riemann-Roch to do the other side. So what do I mean? So I have sides in my mind. I'll draw a picture in a second. Not in a second, after the theorem, after the proof. So the next corollary tells us something about how does the high degree divisors look like. And for me, high degree, you will see in a second why, it's degree 2g minus 2. So corollary 4, corollary 3 talked about degree 0 divisors, right? It kind of completely characterized it, really. And now we are going to characterize degree 2g minus 2 divisors. The 2g minus 2 comes from the fact that degree is 2g minus 2 for the canonical divisors, you'll see. But these are the extreme points for me, 0 and 2g minus 2. Okay, you'll see why, but the corollary tells you that if you have a divisor of degree 2g minus 2, well, maybe it is canonical. By the way, right, we said that the canonical divisor, if you are a canonical divisor, then that's your degree, and the dimension is g, if I remember correctly. But definitely this degree. So what I'm saying is, if this is your degree and you are not canonical, then the dimension is g minus 1. Right, so if you remember, canonical divisors has degree 2g minus 2 and dimension g. And I'm asking, okay, what are other degree 2g minus 2 divisors? Like other in the sense that their degree, this is the degree and they are not canonical. And what I'm saying here is that I know exactly what's their dimension. It's g minus 1. In particular, it's not g, by the way, which makes what I said an equivalence. Right? If you are canonical and this is your degree and this is your dimension, sorry, if this is your degree and this is your dimension, that happens if and only if you are canonical. Because you proved that if you are canonical, then you have this degree and dimension. And this corollary tells you that if this is your degree and you are not canonical, you don't have dimension g. And in fact, I know exactly what your dimension is. It's g minus 1. Okay. And the proof is kind of we use that in Riemann-Roch and kind of invert it, reflect it. So let me show you. So just maybe you should have Riemann-Roch somewhere. And I don't want to put it at the bottom because it's disrespectful. So let's put it here. Yeah. You know, maybe at the same time, I'm just going to erase the whole thing. So Riemann-Roch tells us that the dimension of A is the degree of A, for every A, I mean, plus 1 minus G plus the dimension of C minus A. Right? That's the theorem. And now I'm going to plug a kind of somewhat annoyingly C minus A to A. Okay, so you'll see. So let's apply. So plug. So maybe I should call it B or something, but you'll get it. A equals C minus A in Riemann-Roch. So what does it tell us? I mean, it works for every A. So it works also for C minus A, right? For every A. So it tells us that the dimension of C minus A is the degree of C minus A. This is just a way to see the degree of C minus A somewhere. Plus 1 minus G plus the dimension of A. I should write C minus A for that sake. But that's generally true. Now, when A has degree 2G minus 2, also C has degree 2G minus 2. So this is 0 because deg A and deg C has degree 2G, both are 2G minus 2. Deg A by assumption and deg C in general. So that's 0. Right? Am I wrong? Yeah, that's okay. Sorry? Degree. Yeah. Like that. Good. So yeah. So we get that. Let me just write it here. We get that the dimension of C minus A is 1 minus G plus the dimension of A. In this particular case of A has degree 2G minus 2. Now, what I claim is, first of all, note that C minus A is not principal, right? Because if it is, I mean, if C minus A is principal, it means that it equals some principal divisor. And that means that A minus C, no, sorry, A is C minus X, just moving things around a little bit. Now, that's an element, right? So A is C minus X, and this is an element in the class of canonical divisors, W. No, I'm kind of continuing there. Yeah, sorry, I shouldn't. So we know that. And now by the previous thing we did, the degree of C minus A is 0. But let me just, sorry, I don't remember what correlate is. Yeah, no, correlate is something that we know, right? The degree of C minus A is 0 because the degree of both of them is 2G minus 2. And therefore, I'm still in these brackets by claim, it's not a brackets anymore, really, it's 30% of the proof. By claim 3, the dimension of C minus A is 0. Claim 3 told us, sorry, that's what I wanted to look at. Claim 3 told us that, claim 3 is gone. It was about the degree 0 divisors. Sorry. 7, yeah. Claim 3 told us that if you have a, so what's claim 3? It told us that, the second bullet told us that if you have a divisor B, we call it A there, but then here of C and A, if, just as a reminder in these brackets, if the degree is 0 and B is not principal, right, it's part of the characterization of degree 0, when the dimension of B is 0, right, you remember for this annoying fact that appeared here? So C minus A, you see C minus A has degree 0, because both C and A has degree 2G minus 2. And the dimension, sorry, why C minus A is not principal? Now I stopped the thing. So now I'm continuing assuming that it's not principal, so I'm confused. Sorry, note that C minus A is not principal. Yeah, as otherwise A would be canonical. Right, we assume that it's not canonical. So we took a non-canonical divisor. And if C minus A would have been principal, it means that A is C minus X, and C minus X is an element in this class. Right, sorry, my bad. That's the whole principality thing. Right, if A cannot be, because A is not canonical, this thing cannot be principal, right? The difference between these two cannot be principal because this one is in the canonical class and that's not. So that's what I meant here. Exactly, of excess of like principal divisors. Yeah. Right. Yeah. So that's why. So we know that. Sorry, we know that C minus A is not principal because A is not canonical, and C is. So the difference cannot be a principal divisor. Now continuing on. Sorry. Now, because by corollary 2, regardless of that, orthogonal to that, we know that the degree of C minus A is 0 because that's 2G minus 2 and that's 2G minus 2. And now by claim 3, because we know that C minus A is not principal, and we know that the degree is 0, we are in this situation, right? The degree is 0, dimension, this is not a principal divisor, so the dimension is 0. So that's what I wanted to say. Good, so dimension is 0. So this is 0, and indeed, dim A is G minus 1. This is what we wanted to prove. So after you look at this, you plug it back here, or you plug this back here. This is 0, and so dimension of A is G minus 1. Okay?
So still in second principle, and then how do you get to the rest?
Right, so okay. Yeah, good. So are you fine with C minus A not being principal?
Yes.
Okay. So now let's look at C minus A further. So it's not principal, okay. Its degree is 0 because it's a difference of 2 degree 2G minus 2 divisors. Its dimension, yeah, no, corollary to, I don't know what. Of C is 2G minus 2, yeah, right. We forgot because you already know that so well. Right, the corollary 2 tells you the degree of C is 2G minus 2. Yeah, right. And now, by claim 3, so claim 3 tells you that if you're looking at degree 0 divisor, our divisor is C minus A. You're looking at such a divisor, and it's not principal, and indeed C minus A is not principal, then the dimension of that divisor is 0. All right, so the dimension here is 0, and then you plug it here. Yeah, to 0. Right, by reflecting using C. Exactly, yeah, that's the point. Yes. And right, so one more, just not even one little corollary or just a summarize of this, and then let's do a picture that will, I think, will gather all of this together in a nice way. Because some of it were used in others, and it's hard to make a clear picture out of what I'm trying to say here. So lemma 5 tells you that, yeah, now we really do have a characterization of canonical divisors. So A is a canonical divisor in this class if and only if the degree is 2G minus 2 and the dimension is G. Right, we proved that this direction we just proved initially, we just computed, we took a canonical divisor and computed its degree and dimension using Riemann-Roch. And in the other direction, this is what we just did right now. That's what I kind of said before. In the other direction, if the degree is 2G minus 2, and you are not canonical, then the dimension is G minus 1. In particular, it's not G. Right, this is more information. It would have been enough to have when dim A is not equal to G. That's more information. And in fact, you can just, if you want, that's enough for characterization. That's what you use. Now you know exactly what are the canonical divisors. But if you want, you can use the seemingly weaker, so it's easier to verify, similarly weaker requirement. Just because we know exactly here the dimension. All right, so this implies that. That clearly implies that. That's kind of obvious because it's not equal. That's logic. And this implies that, but by the corollary. So if you want to figure out whether a divisor is canonical, and you know the genus, then right, when you check the degree, and then you can check just the dimension is not G minus 1 if you want. It's slightly easier than checking the dimension is G, but not really because it can only be either these two, one of these two, for degree 2G minus 2. So let me draw the picture. I think that will help. Oh, there is, sorry, no picture yet for you. Two more. I mean, we did 0, we did 2G minus 2. Now let's get below 0 and above 2G minus 2, and then we'll have the picture. 0 and 2G minus 2 is exactly the place that we almost understand, and below 0 and above 2G minus 2, we understand completely. And in the middle, we don't understand anything in general. Where is the purple one? Quit. Do you see a purple? I love the purple. No, yeah? Nice try, yeah. So claim 6. So claim 6 is obvious. So then you have claim 7, I guess. So claim 6 you already know. And we proved it when we analyze Doppler codes. So if the degree of A is smaller than 0, then the dimension of A is 0. I'm just recapping that. We know that. That's how we analyze distance of Doppler codes. Maybe. So you can try to fill the one-line proof. And the other corollary, which is nice, if the degree of A is larger than 2g minus 2, then the dimension we know exactly. We lose everything we can. Like, we know the degree minus dimension is at most g minus 1. And what this claim tells us, it should be elevated. It is elevated. It is a corollary. Good, yeah. It was elevated. I just copied claim. It is an important corollary. It tells you that we completely understand high-degree divisors. We know exactly their dimension. Once you go over 2g minus 2, that without equality, then you lose everything. Degree minus dimension is the maximum loss possible. Like, the degree is so large that you already encoded all the algebraic dependencies already. So let's prove that, and then there is the picture that summarizes all of those. But you see, all of those are like easy corollaries for Riemann-Roch. Just plug A equals C, A equals C minus A, plug it down. So again, we'll do the C minus A Riemann-Roch theorem. Like, so we know that generally dim C minus A. I mean, if you want to, yeah, that's what we did before. I just plug in C minus A instead of A, because it's for every A. Right, so the last thing is dim of C minus A, but it's A. Now, we know by corollary 2 that the degree of C is 2g minus 2. So what do we know? We know that the degree of C is 2g minus 2, and we know that, therefore, the degree of C minus A is smaller than 0. Right? I took A, which has higher degree than 2g minus 2. So the degree of C minus A is the difference, which is negative. And then this claim tells us that there is nothing in the Riemann-Roch space. So by claim 6, it means that the dimension of C minus A, which appears here, is 0. There's nothing there. Too many requirements. So this thing is 0 because of that. Right, and that's it. I mean, now the degree splits and we can see what we get. Right, so we got that 0 is equal to the degree of C minus A, but that's the degree of C minus the degree of A, plus 1 minus G plus dimension of A. And dex is 2G minus 2. Right, so you can see that the degree minus dimension, if you take the degree and dimension to the other side, the deficiency, so-called, is 2G minus 2 minus G plus 1, which is G minus 1. Yeah. Maximum possible deficiency. Yeah, because initially you don't get all the algebraic relations. But as the divisor goes larger and larger, after some point, 2G minus 2, you see all of them. So you get all the deficiencies, all the algebraic relations. You got, right. And there are like G of them, essentially. That's what it says here. So here's the picture. So we have the picture of the degrees. So these are the line of degrees. And you have 0 and like negatives. And turns out 2G minus 2 is an important number. And 2G minus 1. And now what I'm saying is that, so this is the degree line, right? So what we're saying is that if the degree is smaller than 0, like strictly smaller, so minus 1, so here you have nothing. Dimension is 0. That's this thing. My dimension is 0. That's easy. That's not hard. If the degree is larger than 2G minus 1, so with equality possibly, then we know exactly that the degree minus dimension is G minus 1. We know exactly what it is. Now, at 0, we had two possibilities. Either you are a principal divisor, so all of the divisors in the world can be split to principal and non-principal in degree 0, because there are no non-zero degree principal divisors. So principal divisor sits here, and here you have principal divisors and potentially non-principal divisors. But the principal divisor has dimension 1, right? We know that. And the non-principal has dimension 0. Sorry, I should have written it here. So the non-principal has dimension 0. That was the weird claim that appeared here. If the degree is 0, and if you are not canonical, the dimension is 0. So we also understand degree 0 divisors completely. 2G minus 2, it's kind of a dual map to that. If you are a canonical divisor, then we know that the dimension is G. And that's an if and only if, and not only that, if you are not canonical with that degree, then the dimension is G minus 1. Right, so high degree divisors and low degree divisors, we understand. Even here, we kind of understand everything. And in the middle, it really depends on the function field. I mean, this holds true for all function fields of the same genus. Here, it's not just a property of the genus that plays a role. For different function fields, you get different points here. In some, you have small degree divisors, in some you don't have. And maybe as an example, let's consider the rational function field and find a principal divisor, a canonical divisor there. So, right. So let's see. Let's find a canonical divisor of the kx. So we know that to find a canonical divisor, we just need to find a divisor. It's actually quite easy. I mean, I don't know. With degree 2G, if you know the genus at least, maybe easy, and dimension G, or at least not G minus 1, right? Generally speaking. So in kx, like in the function field kx over k, rational function field G is 0. So we want A with degree minus 2 and dimension 0. Right? Just plug in G equals 0. And you can find several of those. But a good example would be minus 2 times p infinity. Right? It has degree minus 2 because this is a degree 1 prime divisor. So altogether, the degree is minus 2. And it has dimension 0 because it's a negative divisor. There's nothing there. This is discord. And you can look at it and you can say, like, weird. I don't know if you expected this in all of the discussion, why it like disappears in kx. Yeah, so in the notes, there is a little bit of a explanation about that with differentials, like the usual differentials. But let me not do it because I didn't talk about it enough. So good. And the last thing we can get from Riemann-Roch kind of easily is the strong approximation theorem. So we had the weak approximation theorem, which I didn't prove here. I proved it in the video. And the same is going to happen. I already recorded it, so it happened for the strong approximation theorem. And the strong approximation theorem tells you a stronger statement that if you have a bunch of places that you want to be close, you want a function that is close to some prescribed functions, finite set of functions up to some numbers, then the weak approximation theorem told you can do that, but all hell breaks loose outside of this set. And the strong approximation theorem tells you that you can also specify a dummy prime divisor, Q, such that the function that you found, all the poles are in that Q. So everything is well behaved outside of Q. This is the garbage bin. You throw everything to Q. I'm not going to state it because we're not going to need it, but it's here, and the proof will be in a video if you want. If you want to look, you don't have to look at it. It's just a nice application of Riemann-Roch. Question so far? Yeah, so this is a canonical divisor of the rational function field. Plus a principal divisor. Yeah. So you can take any function and add the poles and zeros. Just because you see, I don't understand what the deltas and omegas are. I just know I needed to find a degree -2 because G is 0 and a dimension 0 divisor, and I'm done. That's why it's so cool. Like, you don't really need to understand much. Other questions?